Problem 8 says use calculus to determine the absolute max and absolute minimum values of the function below on the interval from 1 to 5. We're looking for absolute extrema, and notice that this interval is closed, so this is going to involve the closed interval method, right, which comes from the extreme value theorem. So the first thing that I do is I calculate the derivative and I try to find my critical values. So the derivative of this function is going to be a product rule, and the derivative of the first term is 3x squared. The second term is x minus 4 cubed. Then I add that to the first term times the derivative of the second term. So this is going to involve a chain rule. So I'm going to have 3 times x minus 4 squared, and the derivative of x minus 4 is just 1. So now I need to set this equal to 0 and solve. But in order to do that, I'm going to clean it up a little bit. So I'm going to factor. I have a 3 in both terms, so I'm going to pull a 3 out front. I have an x squared and an x cubed, so I can remove an x squared. I also have an x minus 4 cubed and an x minus 4 squared, so they both have an x minus 4 squared, so I can pull that out front. And what I'm left with, here I took the 3 and the x squared and one of these x minus 4s, so I'm still left with an x minus 4. In the second term, I took the 3 and all of the x minus 4s, but I'm still left with 1x because I only took 2 of them. So now, if I simplify this one step further, I have 3x squared times x minus 4 squared times 2x minus 4. Now I need to set each piece of this equal to 0 to figure out what my critical values are. So 3x squared equals 0 returns x equals 0. X minus 4 squared set equal to 0 returns x minus 4. And 2x minus 4 equals 0 gives me x equals 2. Now I need to compare them to my interval of 1 to 5. So my interval is here. So this is not a critical value because it's outside of my interval, but 2 and 4 are. If this was a rational expression, I would also need to check anywhere that the derivative did not exist. So I'd separately set the denominator equal to 0 to look for that. But that was not an issue in this problem. So now we're ready to do the closed interval method. And we make a table of values. It is very important that you not put a y here. It is true that these will be y values, but because we do so many different tests in this course, sometimes we plug values into f, sometimes we plug them into f prime, and sometimes we plug them into f double prime. So the best rule here is to always write the function that you're plugging these x values into so we know what you did. So we start with our endpoint of 1, any critical values that we found that fell inside our interval, and then we end with the final endpoint. We're plugging these into our original function, so that's going to be negative 27 when we plug 1 in. We get negative 64 when we plug 2 in. We get 0 when we plug 4 in. And we get 125 when we plug 5 in. So we now scan our list for the lowest and highest y values that we see. So this is going to be where our absolute minimum is, and this is going to be where our absolute maximum is. So it's always a good rule of thumb to report back your absolute max and min as the entire point. So it's almost like you're giving the address on the function of where it is. So f of x has an absolute minimum at 2, negative 64, and f of x has an absolute maximum at 5, 125.